We're looking at derivatives of trigonometric functions in this video, sometimes called circular functions. And in class, we had a look at the whys and wherefores of these derivatives, and they're presented here as a summary. If you don't have them in your summary book yet, now's a good time to do it. F of x equals sine of x, f dash of x equals cos x, f of x equals cos x, then f dash of x equals negative sine x, f of x equals tan x, then f dash of x equals 1 on cos squared x, otherwise known as sec squared x. And just a reminder that when we use this notation for trig functions, where if there's a little 2 here, like a square here, it really means input the angle, get out the trigonometric value of that angle, and then square the result. Okay, so if we were looking at, for example, the cosine of, the sine of 30 degrees, pi on 6, then sine of pi on 6 is a half, and so sine squared of pi on 6 would be a half squared, which is a quarter. So, having given that as a summary, we're going to go through a bunch of examples just so you get a sense of what is going on, and we'll go from there. And I've deliberately not started off with anything too simple, just so that we can get stuck straight into it. Just a reminder about notation. If you've got an f of x, then you should have f dash of x. If you've got a y, then you should have dy by dx, and you should never use y dash. Okay, so almost always what we're looking for is to apply the chain rule for these kinds of things. So I've got dy by dx for example 1, and I know that sine changes to cosine in its derivative, so I go cosine and leave the inside the same, 3x squared, and I look at the inside and I multiply it by its derivative, and the derivative of 3x squared is 6x. But it's much nicer if we write that bit first, so it's 6x cos 3x squared. And again, after a while, by inspection, you can see what you're doing. So you can see this is going to be a 6x squared. You can see this is going to be cos overall. So you can go straight to this line here. There is no need to write this line if you can see how much more neatly you can write it by putting the inside first. That's absolutely fine. It's not always the case, but it's often the case that just a little bit of stepping back and thinking about it will probably save you a bit of time. Okay, example 2. At first glance, that might look like there's a couple of there's just a couple of layers here. There's in fact 3 layers. There's the square, that's the outer layer, because we square sine of this. Then the next layer down is sine, and then the next layer down is this here. And things are being made more complicated by having 2 outside of. Technically speaking, what I'm about to do, you don't need to do, but I feel more comfortable if I just expand first before I go any further. So that would be 2x minus 2 pi on 3. Again, technically speaking, don't have to do that. Alrighty, now we'll go for it. So we deal with the square first. So the 2 comes down, and we're left with sine to the power of 1 now. So it's just sine of 2x minus 2 pi on 3. That's the outer shell done. Next shell down is sine of 2x minus 2 pi on 3. And the sine of 2x minus 2 pi on 3 is the cosine of 2x minus 2 pi on 3, like so. And then the next layer down is 2x minus 2 pi on 3, and that is just 2, because 2 pi on 3, even though there's a pi in it, that's just a number. So 2 pi on 3 is a constant, so the constant disappears, and the derivative of 2x is just 2. So that becomes multiplied by 2. So simplifying that, we've got 4 sine of 2x minus 2 pi on 3, cosine of 2x minus 2 pi on 3. And in a different course of study, I'm not too sure whether it's done in special or not, we learn that 2 sine A cos A actually can be simplified as well, but it's not part of this course. So that's about as simple as we can get with what we know. Example 3, sine squared of 2x plus cos squared of 2x is equal to, okay, the outer layer is the square, so we bring the 2 out and we have sine of 2x, and then we multiply it by the inner layer, which is sine of 2x, and that would be cos 2x. And then the third layer in is the 2x, so that would be multiplied by 2. Okay, plus do the same thing with this. The outer layer is the square, so the 2 comes down, and we're left with cos of 2x. And then we've got the inside layer, which is cos of 2x, and that would be negative sine of 2x. And then we've got another layer inside, which is 2x, and the derivative of that is 2, so it's multiplied by 2. So then I'll simplify that, and that will be 2. For this one here, it's 2 times 2 is 4, so we've got 4 sine 2x cos 2x. And in this one here, we've got 2 times 2 is 4. We've got a sine 2x and a cos 2x, but we've also got a negative there. So we've actually got minus 4 sine 2x cos 2x, and 4 sine 2x cos 2x minus 4 sine 2x cos 2x is equal to 0. What? How can that possibly be? Well, the reason why... Oh, I should have put an f dash of x here. Always forget. The reason why is because if we look up to the front here, we get out our toolbox and we try to apply tools to simplify before we have to do something more complicated. Sine squared plus cos squared of the same angle is equal to 1. So a much simpler application would have been to have gone ... f of x is equal to 1, therefore f dash of x is equal to 0. Again, front-loading your thinking with how can I simplify? What does this mean? Can I recognize what this means? Thinking first, applying your full toolkit to simplify, and then using the techniques you need to solve will always win, but only if you are familiar with your toolbox, all of the tools, the trig identities, everything. It only works if you're familiar with them and then you're thoughtful with them. Otherwise, look at this. It does work, but count the number of minutes it takes you to do that compared to do that. But only with practice, practicing using your toolkit will you get to that point. I'll get off my soapbox now. Example 4. Find the equation of the tangent at x equals pi on 3, given y equals, and there's an expression there. Okay, so what do we need for the equation of a tangent? We need a x and y coordinate. We need a gradient. Okay, we have an x coordinate. We do not have a y coordinate. So let's do that first. So we have y is equal to sine. So, or if you like, at x equals pi on 3, y is equal to the sine of 7 pi on 12 minus pi on 3. I'll just make that a common denominator to help me out. 7 pi on 12 minus, let me think, multiply top and bottom by 4. 4 pi on 12. And that is equal to the sine of 3 pi on 12, which is equal to the sine of pi on 4. Okay, so that's that simplified, but that's one of our exact values, right? Sine of pi on 4 is root 2 on 2. So we have root 2 on 2 as our y coordinate. So we've got pi on 3, root 2 on 2 as our xy point. So that's the point that the tangent is touching at. And now we need to work out the gradient so that we can use y equals mx plus c, or y minus y1 equals mx outside of x minus x1. Okay, so step 2 then, work out that gradient. dy by dx is equal to, so we find the derivative of sine, which is cosine of 7 pi on 12 minus x. Find the derivative of the inside, which is negative 1. Again, this is a constant, so it disappears, and the derivative of negative x is negative 1. So simplifying that, of course, that's negative cosine of 7 pi on 12 minus x. And at x equals pi on 3, we will have dy by dx equaling negative cosine, and I'm just going to do the straight simplification here because we've done it on the left-hand side already. Pi on 3 will make this whole inside pi on 4. So it's pi on 4 like so. So that will be equal to negative root 2 on 2. Okay, so we've got our gradient, negative root 2 on 2, and we've got our xy coordinate. So we can say, therefore, I'm going to have to squish it into this. I might actually have to split up a bit, I suspect. Therefore, just a bit of, if you want to, it's kind of helpful to go, which equals mt, which is the gradient of the tangent. So therefore, we have the tangent line is y is equal to negative root 2 on 2x plus c. But we've got our x and y coordinate. So we've got root 2 on 2 is equal to negative root 2 on 2 multiplied by pi on 3 plus c. So we've